Hello friends, welcome to my lecture on critical points of a linear system. Let us consider a linear system of the form dx by dt equal to pxy, dy by dt equal to qxy, where p and q have continuous first order partial derivatives for all the points xy. Such a system in which the independent variable t occurs only in the differentials dt of the left hand side members and not explicitly in the functions pxy and qxy is called an autonomous system. Let us consider the autonomous system given by the equation 1 dx by dt equal to pxy, dy by dt equal to qxy, a point x naught y naught at which both p x naught y naught is equal to 0 and q x naught y naught is equal to 0 is called a critical point or equilibrium point or singular point of the autonomous system. So, if the functions pxy and qxy vanish at a certain point x naught y naught, then that x naught y naught will be called as a critical point of the autonomous system. Now, let us consider a linear autonomous system dx by dt equal to y, dy by dt equal to minus x. This can be expressed as we can write it like this: dx by dt, dy by dt equal to 0, 1, minus 1, 0, xy. So, let us take vector x to be having components xy, then the column vector dx by dt, dy by dt will be equal to dx by dt, and this will be equal to 0, 1, minus 1, 0 and x, okay, or we can write it as x dot equal to ax, where a is the matrix 2 by 2 matrix 0, 1, minus 1, 0. So, the linear autonomous system can be expressed in this form. Now, we know that the solution of this system x dot equal to ax, where a matrix is given by 0, 1, minus 1, 0, okay, can be found easily. This we have discussed earlier, and we know that the system x dot equal to ax, where a is the matrix 0, 1, minus 1, 0 is given by x t equal to C1 into cos t minus sin t plus C2 times sin t cos t, or we can write it as C1 cos t plus C2 sin t and minus C1 sin t plus C2 cos t. So, here C1 and C2 are arbitrary constants. Now, the solution of this linear autonomous system 2 is given by x t equal to sin t by t equal to cos t, if we assume that x 0 is equal to 0 and by 0 equal to 1. So, that means that if at t equal to 0, if x is equal to 0, okay, then what will happen? X t is equal to C1 cos t plus C t sin t. So, this is x t, this is x t equal to x t y t, okay. So, x t is equal to C1 cos t plus C2 sin t and by t is equal to minus C1 sin t plus C2 cos t. So, if we put the condition that at t equal to 0 x is equal to 0, then we will have 0 equal to C1, okay, cos 0 will be equal to 1, sin 0 is 0. So, C1 is equal to 0 and by 0 equal to 1. So, 1 is equal to minus C1 into 0 plus C2. So, we have C2 equal to 1, and therefore, what we will get x, if you put x t equal to 0, okay, and by 0 equal to 1, then x t will be equal to sin t and by t will be equal to cos t. So, if we put the initial condition that is at t equal to 0 x is 0, at t equal to 0 y equal to 1, then the solution of the autonomous system 2 is given by x t equal to sin t. by t equal to cos t. Now this solution x t equal to sin t and by t equal to cos t defines a path. Okay. Let us call that path as C1 in the xy plane. If we take x0 equal to -1, so we have x t equal to sin t by t equal to cos t. X t equal to C, oh no, we have x t equal to C1 cos t plus C2 sin t. This is x t and by t is equal to minus C1 sin t plus C2 cos t. This is the general solution. So x t equal to C1 cos t plus C2 sin t by t equal to minus C1 sin t plus C2 cos t. If you take C at t equal to 0, x0 is equal to -1 and by 0 equal to 0. If we put these conditions, then from here we shall get x t equal to sin t minus pi by 2, okay, sin t minus pi by 2, and here we will get by t equal to cos t minus pi by 2. If you put t equal to 0 here, then sin minus pi by 2 is -1, so we get x0 equal to -1, and when you put t equal to 0 here, we get cos minus pi by 2, which is 0, so we get y0 equal to 0. Now we can see this solution is different from the earlier solution, okay, but it also defines the same path C1. Thus the ordered pairs of functions sin t cos t and sin t minus pi by 2 cos t minus pi by 2 are two different solutions of the system 2, which are different parameterizations of the same path C1. When we eliminate t, we get that see, if we have x t equal to, we get x t equal to sin t, y t equal to cos t. So if you eliminate t, you can get x square plus y square equal to 1, okay, and here also you get x square plus y square equal to 1. So when we eliminate t, we get that the path C1 is a circle, okay, with center at 0 0 and radius 1. Now eliminating the t in this the system 2 gives us, see, we have these equations, dx by dt equal to y, dy by dt equal to minus x. So dy by dx here will be given by minus x over y. So dy over dx is equal to minus x over y, and this gives the slope of the tangent to the path of 2, which passes through the points x y, okay. So this is your 2, dy over, see, dx over dt equal to y, dy over dt equal to minus x. So dy over dx is equal to minus x over y, and therefore this gives us the slope of the tangent to the path of 2 at the point x y, okay, and C1 describes a path of the system 2. So it gives the so which gives the slope of the tangent to the path of 2 passing through the point x y, provided x y is not the origin. Now dy over dx equal to minus x over y gives you x dx plus y dy equal to 0. When we integrate this equation, we get x square plus y square equal to c square, where c is a parameter. So it is a one parameter family of paths in the xy plane, and we see that it describes a circle with center at 0 0 and radius c. So look at this figure, okay, we have here this is path C1, okay, path C1. Now you can see here that the directions on the circles are all in the clockwise direction. Now let us see how we get the direction to be the clockwise direction. See, we have C1, the C1 is the x t equal to sin t, y t equal to cos t, if x0 equal to 0, y 0 equal to 1. So when you take this, Okay, we have here x 0 equal to 0, so at t equal to 0 x is 0, this and y is 1, so this means we have this point 0 1. Okay, and x t is sin t, y t is cos t. So when t increases from say 0 to pi by 2, sin t increases while cos t decreases, that means x increases while y decreases, and both of them are positive. So we move in this direction. Okay, we move in this direction, and when t becomes pi by 2, we get x t equal to 1 and cos t equal to 0. So we reach here, and then when t increases from pi by 2 to pi, okay, the value of sin t, okay, starts decreasing, okay, from 1 to 0 and 1 to from 1 to 0, while y becomes from 0 to minus 1. So this is 0 minus 1 point, and then again we can move and come here. So when t increases further from 3 pi by 2 to 2 pi, okay, we come here, and this is your minus 1 0 point. So you can see here when we take x at t equal to 0 0 and y at t equal to 0 0 1, and then x t equal to sin t and y t equal to cos t, give us the solution path as x square plus y square equal to 1, and the direction on the curve, the circle is in the clockwise direction. Similarly, if you take the other solution x t equal to sin t minus pi by 2, and y t equal to cos t minus pi by 2, the other solution. Okay, then it is another parameterization of the same path C1. Here what we have, at t equal to 0 we have minus 1. Okay, so x is equal to minus 1, so we have here minus 1, and then at t equal to 0 y is equal to 0, so we have this point. Okay, and then when t increases from 0 and goes up to pi by 2, okay, t increases and goes up to pi by 2, sin 0, we get sin 0, sin 0 is 0, so x 0 x t x pi by 2 is 0, and when t is pi by 2 here we get 1. So we are moving in this direction, okay, and reach the point 0 1, okay, and then we have this clockwise direction. Okay, so we are moving along the circle in the clockwise direction. So you can see here the x square plus y square equal to c square describes one parameter family of circles in the xy phase plane, and the direction along the circles is in the clockwise direction. Now the autonomous system 1 could be interpreted as the autonomous system dy by dx by dt equal to pxy and dy by dt equal to qxy. This autonomous system could be interpreted as a system defining a velocity vector field, where bxy, if you take bxy equal to pxy having components pxy qxy, okay, the x component of the velocity vector v is pxy, while the qxy is the y component of v. The velocity vector v is of any point r which describes a path of one defined parametrically y a solution x equal to ft y equal to gt. Okay, so you take any path, okay, of the system 1 which is defined y the solution, x equal to ft y equal to gt, r is a point on that. So then v is the velocity vector. Okay, say for example you take this, okay, so you can take any point r on this, okay, where x is equal to ft y equal to gt. Then this is the velocity vector, okay, velocity vector. So v is the velocity vector, and at a critical point both components of this velocity vector are 0, okay, because we know that at a critical point pxy is 0 and qxy is 0, that means dx by dt, that means both the components, okay, of this velocity vector are 0, and therefore, we say that the point r is at rest. B describes the velocity vector of the point r, the x component and y component, that is pxy and qxy, both are 0 at a critical point, and so we can say that the velocity of vector at the point r is at the critical point is 0, and there at a critical point is 0. So, the critical point is at rest. Now, so critical point is also called an equilibrium point. Now, in particular, let us consider the special case dx by dt equal to by dy dt equal to fxy, which arises from a dynamical system d square x by dt square equal to fxy. You can take dx by dt equal to y here, okay, then dy by dt will be equal to fxy, and we will get this linear system, okay. We get this autonomous system dx by dt equal to y, dy by dt equal to fxy from this dynamical system. Now, at a critical point, we know that pxy and qxy are 0. So, pxy equal to y is 0 and qxy equal to fxy is equal to 0. Now, y is equal to 0 means at the critical point dx by dt is equal to 0 and fxy is equal to 0 means dy by dt equal to 0. So, at a critical point dx by dt is equal to 0 and dy by dt equal to 0, and further, since d square x by dt square equal to dy by dt, you can see from here d square dx by dt equal to y. So, d square x by dt square is equal to dy by dt. Okay. Now, at a critical point pxy and qxy are both zeros, and therefore, y is equal to 0 and fxy equal to 0. So, we get dx by dt equal to 0 and dy by dt equal to 0, and further from the equation dx by dt equal to y, it follows that d square x by dt square is equal to dy by dt, but dy by dt is 0. So, d square x by dt square is equal to 0, and therefore, we can say that the velocity and acceleration of the dynamical system described by the equation 4 are both 0, and thus the critical points of the system 3 are dynamical are equilibrium points of the dynamical system. Now, let us define an isolated point, a critical point x naught y naught of the system 1, that is dx over dt equal to pxy, dy by dt equal to, this is our system 1. So, a critical point x naught y naught of the system 1 is called isolated if we can find a circle with center at the point x naught y naught of some positive radius r such that x naught y naught is the only critical point within this circle. So, if so, you can say this is your point x naught y naught, we will call it an isolated critical point if we can find a circle with center at x naught y naught of radius say r such that inside this circle there is no other critical point. Now, henceforth in our discussion let us assume that every critical point is isolated, and for convenience we shall take the critical point x naught y naught to be the origin. Suppose x naught y naught is not the origin, then by transformation of coordinates xi equal to x minus x naught, eta equal to y minus y naught, the point x naught y naught was transformed into the point x naught y naught is transformed into 0 0 in the xi eta plane, okay, transforms into 0 0 in the xi eta plane. So, without any loss of generality we can assume that the point x naught y naught is the origin. Now, let us assume that C be a path of the system 1 and let x equal to f t, y equal to g t be a solution of 1 which describes C parametrically, which represents C parametrically, and let us take 0 0 to be a critical point of 1. As we have already said, this point 0 0 is an isolated critical point. Now, we say that the path C approaches the critical point 0 0 as t goes to infinity if limit t goes to infinity f t equal to 0 and limit t goes to infinity g t equal to 0. Thus, a point R tracing out C according to equations x equal to f t, y equal to g t approaches to the point 0 0 as t goes to infinity independent of the solution used to represent C. In other words, if C approaches 0 0 as t goes to plus infinity, then 5 is true for all solutions x equal to f t, y equal to g t representing C. So, it is independent of the solution. Now, similarly, a path C1 approaches the critical point 0 0 as t goes to minus infinity if limit t tends to minus infinity f1 t equal to 0 and limit t tends to minus infinity g1 t equal to 0, where x equal to f1 t, y equal to g1 t is a solution defining the path C1. Now, let another definition, let C be a path of system 1 which approaches the critical point 0 0 of the system 1 as t goes to plus infinity, and let x equal to f t, y equal to g t be a solution of 1 which represents C parametrically. Then we say that C enters the critical point 0 0 as t goes to infinity if the limit of the functions g t over f t exists as t goes to plus infinity, or the limit of g t over f t becomes plus infinity or minus infinity as t goes to plus infinity. So, either the limit of g t over f t as t goes to plus infinity is finite, or it is plus infinity or minus infinity. Then we shall say that the path C enters the critical point 0 0 as t goes to infinity. Since g t y f t gives the slope of the line joining critical point 0 0 and a point R with coordinates f t g t on C. Let us see how we get that. Suppose your this is your 0 0 critical point and this is your path, okay, describing C. R is any point here, f t g t, okay. Then the slope, okay, slope of the line O R, okay, this is O, okay, will be g t over f t. So, since g t over f t gives the slope of the line joining the critical point 0 0 and a point R with coordinates f t g t on C, okay, hence by a path C enters the critical point 0 0, we mean that the line joining 0 0 and a point R tracing out C approaches a definite limiting direction as t goes to infinity, okay. So, when a line joining 0 0 and a point R which is tracing out the curve C approaches a definite limiting direction as t goes to infinity, we shall say that the path C enters the critical point 0 0. Now, let us discuss the various types of critical points. The isolated critical point 0 0 of 1 is called a center. If we can find a neighborhood of 0 0 which contains a countably infinite number of closed paths, each of which contains 0 0 in its interior and which are such that the diameters of the paths approach 0 as n goes to infinity, but 0 0 is not approached by any path either as t goes to plus infinity or as t goes to minus infinity. Now, by a neighborhood of 0 0 we mean that it is a set of all points x y lying within some fixed distance d of 0 0. Since an uncountably infinite set always contains a countably infinite subset, the definition of center does not exclude the possibility of an uncountably infinite set of closed paths, each of which contains 0 0 in its interior. Now, let us look at this figure. You can see here these are closed paths, okay. Each path is containing 0 0 inside at its center, okay, and they are approaching 0 0, but you can see the diameters of the paths approach 0 as n goes to infinity, but 0 0 is not approached by any path, okay, as t goes to plus infinity or t goes to infinity, and each path is containing 0 0 in its interior. Here you can see each path is containing 0 0 in its interior, okay, and the diameters of the paths are going to 0, but no path is approaching to 0, okay. So 0 is not 0 0 is not approached by any path, either as t goes to plus infinity or t goes to minus infinity. So here 0 0 is a node. Now let us discuss saddle point. The isolated critical point 0 0 is called a saddle point if we can find a neighborhood of 0 0 such that the following conditions holds. There exist two paths which approach and enter 0 0 from a pair of opposite directions as t goes to plus infinity, and there exist two paths which approach and enter 0 0 from a different pair of opposite directions as t goes to minus infinity. In each of the four domains between any of the four directions in one, there are infinitely many paths which are arbitrarily close to 0 0, but which do not approach 0 0 either as t goes to plus infinity or as t goes to minus infinity. Now you can see here these are two paths, okay. These are two paths which approach and enter 0 0, okay, and there is another two paths, this one and this one, okay. They are in opposite directions. Here you can see the direction is this direction, here this is this direction, this direction. So we have there exist two paths which approach and enter 0 0 from a pair of opposite directions as t goes to plus infinity, okay, like this, as t goes to plus infinity and like this, and there are two paths which approach and enter 0 0 in the opposite directions as t goes to minus infinity. Now you can see these four directions, okay, divide this xy plane into four regions, R1, R2, R3 and R4, okay. So there are four regions, and in each of the four domains between any of the four directions there are infinitely many paths. You can see there are infinitely many paths. These are infinitely many paths, okay. These are infinitely many paths like this. So there are infinitely many paths which are arbitrarily close to 0 0, but which do not approach 0 0 either as t goes to infinity or as t goes to minus infinity. So here 0 0 is a saddle point. Now let us discuss spiral point. The isolated critical point 0 0 is called a spiral point or focal point if we can find a neighborhood of 0 0 such that every path p in this neighborhood has the following properties. P is defined for all t greater than t naught and R for all t less than t naught for some real number t naught. P approaches 0 0 as t goes to plus infinity or as t goes to minus infinity. P approaches 0 0 in a spiral like manner, binding around 0 0 an infinite number of times as t goes to plus infinity or as t goes to minus infinity. So you can see here, okay, this is the spiral, this 0 0 is a spiral point here because the paths are binding around the point 0 0, okay. The P is defined, okay, every path P, you can take any path P, P is defined for all t greater than t naught or some t less than t naught, and it is approaching 0 0 as t goes to plus infinity or it is approaching 0 0, okay. It is approaching 0 0 as t goes to plus infinity or minus infinity, and it is approaching 0 0 in a spiral like manner, okay, like this, a spiral like manner. It is approaching 0 0 in a spiral like manner. So as t goes to plus infinity or minus infinity. Now we come to node. The isolated critical point 0 0 is called a node if there exists a neighborhood of 0 0 such that every path P in this neighborhood has the following properties. P is defined for all t greater than t naught, R for all t less than t naught, for some real number t naught. P approaches 0 0 as t goes to plus infinity, R as t goes to minus infinity, and P enters 0 0 as t goes to plus infinity, R as t goes to minus infinity. Now, so here P approaches 0 0, okay, in a spiral like manner, and it binds around 0 0 an infinite number of times. Here P approaches 0 0, R P enters as t goes to plus infinity, R as t goes to minus infinity, but it does not bind around the point 0 0. So, in the case of node, you can see the path. See, we have P is defined for all t greater than 0 for some real number t naught. P approaches 0 0 as t goes to infinity or minus infinity, and P enters 0 0 as t goes to plus infinity or minus infinity. So, you can see this path, okay, this one, okay, this path AB, okay, and then you can see these paths are approaching to origin, okay, and you will see that the slope of these paths at origin is nothing but the slope of the line AB, okay. So, this is the characteristic of a node. The paths are approaching 0 0 as t goes to plus infinity and minus infinity, and when we discuss later on in detail, we shall see that these paths approach to the origin with the slope of the line AB. With that, I come to the end of this lecture. Thank you very much.